Have you ever felt like a computer staring at a junk drawer? That's kind of what it's like for these machine learning models, trying to learn from all this raw data. So today we got to talk feature engineering, basically turning that data mess into something a computer can actually make sense of.
It's like, imagine a jigsaw puzzle. Pieces are everywhere. Some are missing and others are like upside down, right? Feature engineering is about organizing all those pieces, making the information, the picture hidden underneath, way more clear.
This deep dive is brought to you by the book Feature Engineering for Machine Learning. And honestly, one of the first things that really got me thinking was, how do you even begin to teach a computer about language? It's not like they can just pick up Shakespeare and get it.
It's a huge challenge for sure. One way we try to bridge that gap is by turning words into numbers. And a really common technique is called, get this, bag of words.
Bag of words. Sounds more like something you'd take to the grocery store.
Right. But it actually makes sense. It's like taking all the words from a sentence and just tossing them in a bag. You don't care about the order anymore, just how many times each word shows up. So, this movie is good, and good this movie is, would actually look the same to the computer.
So basically, the computer sees a numerical profile of the sentence, not the actual words.
Exactly. And as simple as it sounds, this lets machine learning models start picking up on patterns. Sentences with similar bag of words, they often have similar meanings. But language, it's got layers, right?
That's what makes it interesting and probably tricky for a computer to really grasp. The book mentioned something called n-grams. Is that where things get a bit more sophisticated?
Yeah, you got it. N-grams, they look at chunks of words, pairs, triplets, you name it. So instead of just not and bad separately, the model picks up on not bad as one unit of meaning, which really captures those nuances of slang or common phrases.
It's like teaching the computer to understand the subtle ways we humans actually talk.
Exactly. But it gets even more interesting. Remember those important puzzle pieces we talked about? Well, some words carry more weight than others, and that's where TF-IDF enters the scene.
Okay, got to unpack that acronym. TF-IDF. What is it, and why should we care about it?
It stands for Term Frequency Inverse Document Frequency. Yeah, it's a mouthful. But basically, it helps us figure out which words are the most important in a given document compared to like a whole bunch of other documents.
So like a word that pops up a lot in one movie review but is rare in others, that might tell us something unique about that film.
You got it. We might think the most common words are the most important, but TF-IDF lets us see that the words that are common in one document, but rare overall, those are often the most telling. Think about like all that technical jargon in a scientific paper really tells you a lot about that specific subject.
That makes total sense. But language isn't just words, is it? We've got city names, colors, all sorts of things that aren't naturally numerical. How does feature engineering handle that kind of data?
Yeah, it's like try to explain what chocolate tastes like if someone's never had it before. How do you even translate that into something a computer can work with?
That's where we bring in things like one-hot encoding. Let's say you've got 3 cities, New York, San Francisco, Seattle. One-hot encoding creates a binary code for each one. So New York might be 100, San Francisco 010, and so on.
So each city, even though it's not a number, gets its own unique code that the computer can recognize.
Exactly. It's a pretty simple idea, but it's powerful for representing categorical data. But where it gets really interesting is when you're not dealing with 3 cities, but say millions of users, each with their own preferences, their own behaviors.
Okay, now we're talking massive amounts of data. The book talked about feature hashing and bin counting as ways to deal with those really huge data sets. What's the magic behind those techniques? So with feature hashing, imagine you have, let's say, 1,000,000 categories. That's a ton of codes to keep track of. What feature hashing does is it uses a hash function to condense those categories into a smaller, more manageable set.
So it's kind of like taking that million-piece jigsaw puzzle and grouping similar pieces together so it's not so overwhelming to put together.
Exactly. It's a bit like using a randomizer, but with a specific purpose. Similar items, they often end up in the same bucket, which lets the model pick up on patterns even with this kind of condensed representation.
That's really clever. What about bin counting? Does that actually involve, like, counting things?
You bet. Instead of just noting if a category is there or not, bin counting tells us how often it shows up, which gives us a much richer picture of the data. So, for example, instead of just knowing someone clicked on an ad, we can see how many times they've clicked on ads like it in the past.
Now that's useful information. It's like the difference between seeing someone glance at a flyer and seeing them actually tear it off the bulletin board because they want to know more. But with all this number crunching going on, Do computers ever get overwhelmed? Because we humans certainly do.
They totally can. Think about trying to make sense of a scientific paper with hundreds of variables. It's easy to get lost in the details, right? And computers can face that same problem with too much data.
That's where dimensionality reduction comes in. I remember the book mentioned this technique called PCA, Principal Component Analysis.
PCA is like finding a shortcut through a really dense forest. It helps reduce the complexity of the data, but it holds on to that essential information.
So instead of getting bogged down in every single detail, PCA helps you find the landmarks, those key pieces of information that guide you through the data.
Exactly. And it's super helpful for visualizing data. Imagine taking a really complex 3D object and projecting its shadow onto a 2D surface. PCA is kind of like that, but for data. It makes it easier to see those hidden patterns and relationships.
Okay, I'm with you. What about when the data isn't so linear, though? Like when the relationships aren't so straightforward. The book mentions something called k-means clustering for those trickier situations.
K-means clustering. Okay, picture this. You walk into a party, and people have naturally formed little groups, right? Maybe based on their interests or their backgrounds or how well they know each other. K-means clustering helps us identify those kinds of clusters in our data.
So even if the connection isn't obvious right away, k-means can help us see that underlying structure, those hidden patterns in the data.
Exactly. It's like grouping stars into constellations. They might seem randomly scattered at first, but K-means helps us see the patterns that connect them.
This is all so incredibly clever. We've gone from turning words into numbers to grouping stars into constellations. But the book also touched on this shift from those handcrafted features to the rise of deep learning. What's the story there?
Deep learning, that's a whole other ballgame. Instead of us telling the computer what features to look for, deep learning models, they learn those features themselves directly from the data.
Wait, the machines are teaching themselves. That sounds amazing and maybe a little bit scary all at the same time.
It's pretty mind-blowing, and it's been revolutionary for things like image recognition, where it's really tough to manually define features that capture all the little nuances of what we see.
I remember the book mentioned some older techniques like SIFT and HOG, which were used for image feature extraction. How do those stack up against the power of deep learning?
Think of SIFT and HOG as those really meticulous artists, you know? They're carefully sketching out every single detail of an image based on things like gradients and edges. Deep learning is more like that art prodigy who just seems to get it. They can grasp the essence of an image and recreate it with amazing accuracy.
So instead of us painstakingly defining every single feature, we're letting the deep learning model figure it out on its own. That's incredible. How does it even do that? What's the magic trick? So before we went away, we were talking about deep learning. These models that almost seem to teach themselves how to understand images, understand data. It's like they've got this artistic intuition, but instead of paintbrushes, they're using algorithms.
It really is a fascinating process. Deep learning models, they learn through this really clever mechanism. It's called backpropagation. Okay, so imagine the model is like practicing archery, right? It shoots arrows at a target, and with each shot, it sees how far off it was and then adjusts its aim.
So it's like the model is getting feedback, and it uses that feedback to get better, to improve its understanding of the data over time.
Precisely. The difference between what the model predicts and the actual target, that's the error. And backpropagation, that's how the model tweaks its internal settings, all those connections, to make that error smaller.
So it's like it's learning from its mistakes, just like we do, but instead of like getting a bad grade, it gets a high error and knows it needs to study harder.
Exactly. And the more it practices, the more data you feed it, the better it gets at hitting that target, at making those accurate predictions. That whole process, that trial and error, learning from feedback, that's really the key to the power of deep learning.
This whole world of deep learning, of feature engineering, it's really changing things in so many fields. But for those of us who aren't, like coding these complex models ourselves, what's the takeaway? How can we actually use these ideas?
You know, that's a really important question. Feature engineering, at its heart, it's all about understanding the story that your data is trying to tell. It's about finding that right language, that right representation to share that story with the machine learning model.
So even if we're not the ones building the models, understanding these concepts, it helps us make sense of our own data, whether it's customer info or market trends, or even just our own personal health stats.
Absolutely. It's like knowing which questions to ask, what patterns to look for to unlock those insights hidden in your data. And the really cool thing is you don't need to be a math whiz to do this. There are more and more tools out there that make it way easier to play around with these feature engineering techniques.
That's really great to hear. So as we wrap up our deep dive here into the world of feature engineering, what's that one big thought you want to leave our listeners with?
Don't be afraid to get your hands dirty with data. It doesn't matter if you're working with spreadsheets, databases, or even just things you notice in the world around you. There's always something to learn by trying out those feature engineering principles.
It's about asking questions, experimenting, looking for those hidden patterns that can help us understand things in a deeper way.
Exactly. So go out there and unlock those insights.
I love it. And that is a perfect note to end on. Thanks for joining us on this deep dive into the world of feature engineering. Until next time, keep those data fires burning.